Hello friends, welcome to my lecture on solution of homogeneous linear system with constant coefficients. We shall discuss the case of equal roots of the characteristic equation in this lecture. So, if the characteristic polynomial of a matrix A does not have n distinct roots, then A may not have n linearly independent eigenvectors. For example, let us consider the matrix A equal to 1 1 0 0 1 0 0 0 2. Then you can see that it is an upper triangular matrix, its diagonal elements are therefore its eigenvalues. So, the diagonal elements are 1 1 2 and therefore, it has eigenvalues 1 1 2. Okay. Now, corresponding to eigenvalue lambda equal to 1, if you find the eigenvector, then what you get? A minus I into B equal to 0. So, you subtract identity matrix from A and what you get is 0 1 0 0 0 0 and then 0 0 1. So, this is B 1, B 2, B 3 and you get 0 0 0 here and what you get is okay. So, B 1 into 0, B 2 into 1 plus B 3 into 0 equal to 0. So, you get B 2 equal to 0 and then second equation is 0 equation, third equation gives you B 3 equal to 0 and thus B equal to B 1, B 2, B 3 reduces to B 1 0 0. Okay. Or we can take we can write it as B 1 times 1 0 0. So, taking B 1 equal to 1, you have an eigenvector 1 0 0 corresponding to eigenvalue lambda equal to 1 and for lambda equal to 2 similarly you can find an eigenvector 0 0 1. So, you see here that we do not have 3 linearly independent eigenvectors corresponding to the eigenvalues 1 1 2, only 2 linearly independent eigenvectors we have. So, how to find n linearly independent solutions of the vector differential equation Ax equal to x dot equal to Ax, that is the question. Okay. So, thus if you consider the vector differential equation x dot equal to Ax, it will have only 2 linearly independent solutions of the form e to the power lambda t corresponding to lambda 1 equal to 1. We got one vector which is 1 0 0. So, one solution you get and then corresponding to lambda equal to 2 you got one eigenvector 0 0 1. So, you get another linearly independent solution of the form e to the power lambda t into b. Now, therefore, we need to find a third linearly independent solution, because in order to write the general solution of the vector differential equation x dot equal to x, we need to have n linearly independent solutions of this equation and here A is a 3 by 3 matrix. So, we need 3 linearly independent solutions. Now, in general suppose that the n by n matrix A has only k less than n linearly independent eigenvectors, then the differential equation x dot equal to Ax has only k linearly independent solutions of the form e to the power lambda t into b. Therefore, we need to find n minus k linearly independent solutions in order to write the general solution of the vector differential equation x dot equal to x. Now, we know that if you take the scalar first order differential equation x dot equal to Ax, where A and x are scalars, then x t equal to c times e to the power a t is a solution of this equation, that you can see it easily. You have dx by dt equal to Ax. So, that gives you dx by x equal to a dt and so when you integrate we get ln x equal to ln t a times ln t plus constant, let us take ln c, then you get x equal to c times you have not ln t, it is a t. Okay. So, ln x equal to a t plus ln c. So, x equal to c times e to the power a t. So, x equal to c times e to the power a t is the solution of this equation. Analogously, x t equal to e to the power a t into b is a solution of the vector differential equation x dot equal to Ax for a constant vector B. Let us see how it is the solution of this vector differential equation. First of all, let us see the definition of e to the power at. E to the power at, where A is a n×n matrix, is defined as I plus at plus a square t square by 2 factorial and so on, a to the power n, t to the power n by n factorial and so on, where I is an identity matrix of the same order as A, that is I is the identity matrix of order n. Now, it can be shown that the infinite series which is giving e to the power at, it converges for all t and can be differentiated term by term. Now, if you find d to the d over dt of e to the power at into b, what you get? You see d over dt of e to the power at into b. So, this is equal to d over dt of e to the power at means I plus at plus a square t square by 2 factorial and so on, a to the power n, t to the power n by n factorial and so on into b, where b is a constant vector. So, when we differentiate with respect to t, what we get? I is a this is independent of t, so this will be 0. So, we get a t. When we differentiate this with respect to t, we get a plus a square into 2t by 2 factorial into 2t by 2 factorial and then and so on, a to the power n into n t to the power n minus 1 by n factorial and so on b. Okay. Or I can write it as a into I plus, here we have at, then we have a to the power n minus 1, t to the power n minus 1 over n minus 1 factorial and so on b. Okay. So, this is e to the power at. So, we get a into e to the power at into b, that is the derivative of e to the power at into b. So, d over dt of e to the power at into b is a times e to the power at into b, and since we can write it as e to the power at okay, into a b. So, what we get we have to write it as this is a e to the power at into b. So, what we have? D over dt of e to the power at into b is a into e to the power at into b, and therefore, our differential equation is dx by dt equal to ax. So, in this, if we replace x by e to the power at into b, what we get is d over dt of e to the power at into b equal to a times e to the power at into b. That is what we get here. So, e to the power at into b is a solution of the vector differential equation 1 for every constant vector b. Now, we can easily show that e to the power at inverse is equal to e to the power minus at, and e to the power at plus s equal to e to the power at into e to the power as, e to the power at plus bt equal to e to the power at into e to the power bt if ab equal to ba. This we can see very easily. See, e to the power at into e to the power minus at. If you write, what we get? I plus at plus a square t square by 2 factorial and so on, and then we multiply by e to the power minus at. So, I minus at plus a square t square by 2 factorial minus a cube t cube by 3 factorial and so on. Okay. So, we multiply by I first. So, I plus I at plus a square t square by 2 factorial and so on, then minus at. So, we get minus at, then we multiply minus at here. So, minus a square t square, then we multiply minus at here. So, minus a cube t cube by 2 factorial and so on. Then you multiply by a square t square by 2 factorial. So, you get a square t square by 2 factorial. okay, then a cube t square by 2 factorial, and then you multiply by a square t square. So, a 4 t 4 by 2 factorial square, and so on, you get like this. So, a t will cancel with a square t square by 2 factorial plus a square t square by 2 factorial is a square t square. So, it will cancel with a square t square. Similarly, a cube t cube by 3 factorial, okay, minus a cube t cube by 2 factorial, and then minus a cube t cube by 3 factorial. So, what we will get, all the terms will cancel except I, and what we get is e to the power a t into e to the power minus a t equal to I. So, we can say that e to the power a t inverse is equal to e to the power minus a t. And similarly, if you multiply the series for e to the power a t and then the series for e to the power a t, you will get the series for e to the power a t plus s. But here when you multiply e to the power a t into e to the power b t, then you need a b equal to b a in order to get e to the power a t plus b t. So, e to the power a t plus b t is true only if e to the power a t is into e to the power b only if a b equal to b a. So, e to the power a t plus b t is e to the power a t into e to the power b t provided a b is equal to b a. Now, let us look at these two matrices, a minus lambda I, okay. A minus lambda into lambda I is same as lambda I into a minus lambda I. Why? Because a minus a lambda I is lambda a, okay, and then minus lambda I into lambda I is lambda square I square. So, we get lambda square I. So, left hand side is this and right hand side is what? Lambda into I a, that is lambda into a, and then lambda I into lambda I is minus lambda square I square. So, lambda square I. So, left hand side and right hand side are same. So, a minus lambda I into lambda I is equal to lambda I into a minus lambda I. So, a minus lambda I and lambda I commute, okay, where lambda is constant. Now, using this property, e to the power a t into b, e to the power a t into b is e to the power a minus lambda I into t plus lambda I t, okay. E to the power a t is equal to e to the power a minus lambda I t plus lambda I t. Now, use this property a minus lambda I and lambda I, since they commute, okay, since they commute we can write it as e to the power a minus lambda I into t into e to the power lambda I t. So, e to power a t can be written as e to power a minus lambda I into t into e to power lambda I t, because a minus lambda I and lambda I commute, and you are using this property e to power a t plus b t is equal to e to power a t into e to power b t. Now, e to the power lambda I t is equal to e to the power lambda t into b. This we can see very easily, e to the power lambda I t. Let us write e to the power lambda I t into b. This is equal to we have I plus lambda I t plus lambda square I square t upon 2 factorial and so on, and into b. So, what you get is, so this is b plus, okay, I b equal to b, and then lambda t into b, I b equal to b again, then lambda square I square t square here, okay. So, lambda square t square I square into b is b. So, lambda square t square by 2 factorial into b and so on, or I can write it as 1 scalar 1 plus lambda t plus lambda square t square by 2 factorial and so on into b, which is equal to e to the power lambda t into b, okay. So, e to the power lambda I t into b is e to the power lambda t into b, and therefore, e to the power a t b equal to e to the power a minus lambda I t into e to the power lambda t into b. Now, e to the power lambda t is a scalar quantity. So, we can write it outside this matrix, this matrix, e to the power lambda t into e to the power a minus lambda I t b. Okay. So, ultimately what we have, e to the power a t b is equal to e to the power lambda t into e to the power a minus lambda I t into b. Okay. Now, suppose a minus lambda I m b equal to 0, a minus lambda I m b equal to 0 for some integer m, then e to the power a t b is equal to e to the power a t b equal to e to the power lambda t into b plus t times a minus I b plus and so on t to the power m minus 1 a minus lambda t raised to the power m minus 1 into b and then m minus 1 factorial. This we can see from the previous equation. We have e to the power a t into b is equal to this. Okay. So, we have a to the power a minus lambda I into b, a minus lambda I into t into b. Okay, this is what we have, e to the power a t into b, e to the power a t into b equal to e to the power lambda t into e to the power a minus lambda I into t into operating on b. So, this is equal to e to the power lambda t, and let us write the expansion series for this. So, I plus a minus lambda I t plus a minus lambda I whole square t square by 2 factorial a minus lambda I whole cube t cube by 3 factorial and so on. Okay. T to the power m minus m a minus lambda I raised to the power m minus 1, let us write m minus 1 b upon m minus 1 factorial, and then we have t to the power m a minus lambda I to the power m b upon m factorial and then so on t to the power m plus 1 a minus lambda I to the power m plus 1 b upon m plus 1 factorial and so on. So, here wait, I should not have written b we can write outside here. Okay. So, then what happens is when this series operates on b, you get b plus a t times a minus lambda I into b, you get e to the power lambda t b plus a minus lambda b plus t times a minus lambda I b plus t square by 2 factorial a minus lambda I whole square b and so on. We get t to the power m minus 1 a minus lambda I to the power m minus 1 b upon m minus 1 factorial, and then we have t to the power m a minus lambda I to the power m b upon m factorial and so on. Now, if b satisfies a minus lambda I m b equal to 0 for some m, for some positive integer m, then what will happen? This term will be 0, t to the power m into a minus lambda I to the power m b m factorial equal to 0, and after this we will have t to the power m plus 1 a minus lambda I to the power m plus 1 b upon m plus 1 factorial. That term will also be 0 because you can operate on this equation by a minus lambda I, so that you get a minus lambda I to the power m plus 1 b equal to 0. So, if a minus lambda I to the power m into b equal to 0, then a minus b I to the power n b equal to a minus lambda I to the power n be equal to 0 for all n greater than or equal to m plus 1. So, this a minus lambda I to the power m into b equal to 0 implies this equal to 0 for all n greater than or equal to m plus 1. So, this series will then reduce to this series. Okay. All terms starting with the power of t to the power the power of t as m and more, okay, will vanish, and we will have e to the power a t into b equal to e to the power lambda t b plus t times a minus lambda I into b and so on t to the power m minus 1 a minus lambda I to the power m minus 1 b over m minus 1 factorial. So, there will be only m terms in the inside the bracket. Now, let us see how we can find n linearly independent solutions of the vector differential equation x dot equal to a x. So, in order to find additional solutions, suppose we have k solutions in linearly independent solutions. In order to find n minus k solutions, we pick an eigenvalue lambda of a and find all vectors b for which a minus lambda I whole square b equal to 0, but a minus lambda I b is not equal to 0. Okay. So, for each such vector e to the power a t into b equal to, we have seen just now, e to the power a t into b equal to e to the power lambda t into e to the power a minus lambda into t into b will reduce to e to the power lambda t into b plus t times a minus lambda I into b, because we are assuming that a minus lambda I whole square b equal to 0. So, here m is equal to 2, and this means that only b plus t times a minus lambda I into b will remain inside the bracket, all other terms will vanish. So, we will have e to the power a t into b equal to e to the power lambda t into b plus t times a minus lambda I into b. This will give us an additional solution of x dot equal to a x. Now, we do this for all eigenvalues lambda of a. If we still do not have enough solutions, that is we do not get all n solutions, then we find all vectors b for which a minus lambda I raised to the power 3 b equal to 0, but a minus lambda I whole square b is not equal to 0. For such a vector b, e to the power a t into b will then give you e to the power lambda t into e to the power a minus lambda I into t into b, which will reduce to this. Okay. So, this e to the power a minus lambda I into t v will give you this expression inside the bracket, all other terms will vanish. So, e to the power a t into b will be e to the power lambda t b plus t times a minus lambda into b plus t square by 2 factorial a minus lambda I whole square b, which will give us an additional solution of x dot equal to a x. Now, proceeding in this manner, we obtain n linearly independent solutions of the equation x dot equal to x. So, let us now take an example where x dot is equal to a x is given. A is a 3 by 3 matrix. So, our aim will be to determine 3 linearly independent solutions of this vector differential equation. So, here a is equal to 1 1 0 0 1 0 and 0 0 2. Okay. Let us note that A is a triangular matrix, upper triangular matrix. So, the eigenvalues of A are the diagonal elements of A. The diagonal elements of A are 1 1 2, these are the diagonal elements. And this is an upper triangular matrix. So, the diagonal elements are the eigenvalues of A. Okay. The diagonal elements of an upper triangular or lower triangular matrix are its eigenvalues. The diagonal elements of A are 1 1 2. So, we have the eigenvalues of A 1 1 2. Now, let us find the eigenvector for lambda equal to 1. So, we have to consider a minus I b equal to 0. We have this 1 1 0. Let us find a minus I b equal to 0. So, what we will get? This will give you 0 1 0 0 0 0 and then 0 0 1. So, here you can see B 2 is equal to 0 and B 3 equal to 0. So, we get the eigenvector B as B 1 0 0 and you can take it as 1 0 0. So, we get corresponding to eigenvalue lambda equal to 1, we get an eigenvector 1 0 0 and therefore, we can have one solution of the equation x dot equal to A x. We know that x t equal to e to the power lambda t into b. Okay. If lambda is an eigenvalue and b is the corresponding eigenvector of the matrix A, then x t equal to e to the power lambda t into b is a solution of x dot equal to x. So, one solution x 1 t will be equal to lambda is 1 here. So, e to the power t and the eigenvector we have taken as 1 0 0. So, we have one solution e to the power t into 1 0 0. Now, to find the other linearly independent solution, now one solution we shall get corresponding to lambda equal to 2, okay. But corresponding to lambda equal to 1 we have got only one linearly independent solution. So, let us find one more solution corresponding to lambda equal to 1. So, what we get to do is to find the other linearly independent solution, we find those vectors B for which A minus lambda I whole square B equal to 0 such that A minus lambda I B is not equal to 0, where lambda is equal where lambda is equal to 1. This we are doing for lambda equal to 1. So, what we will do is let us find A minus lambda I whole square, lambda is 1 here. So, A minus I whole square B equal to 0 gives you, if you write A minus I matrix. So, A square will be equal to 1 1 0 0 1 0 0 0 2 and you multiply 1 1 0 0 1 0 0 0 2. So, what you get when you multiply 1 0 0 here, what you get is 1 0 0 1 1 2 0, when you multiply you get 1 1 0, when you multiply you get 1 plus 1, that is 2, and 1 1 0 here we get 1 into 0 0 1 into 1 1, okay, and then 1 1 0 we multiply to 0 0 2. So, we get 0 and then 0 0 2 when we multiply we get 0 here and 0 0 2 we multiply here we get 0 and here we multiply we get 4. So, A square this is A minus I need not, I do not need this, I need A minus I whole square, sorry. So, I need A minus I whole square. So, A minus I whole square is 0 1 0 0 0 0 0 0 1 and 0 1 0 0 0 0 0 0 1. So, let us see what it is. First column is 0 0 0. So, when you multiply to the all rows here, you will get the first column as 0 0 0 and then 1 0 0 you multiply. So, 1 0 0 will give 0 here, 1 0 0 will give 0 here, 1 0 0 will give here again 0 and 0 0 1 you multiply you get 0, here you multiply you get 0 and here you multiply you get 1. Okay. So, we get this matrix. So, A minus lambda A minus I whole square B equal to 0 gives you 0 0 0 0 0 0 0 0 1 B 1 B 2 B 3 equal to, so what we get B 3 equal to 0 and so B is equal to B 1 B 2 B 3. So, B 1 B 2 are arbitrary and we get B 3 as 0 here. Okay. Now, I can write it as B 1 times 1 0 0 plus B 2 times 0 1 0. So, one eigenvector corresponding to one solution for A minus lambda I whole square B is can be taken as 1 0 0, the other solution can be taken as 0 1 0. But if you take 1 0 0, then we have seen A minus I 1 0 0 equal to 0, A minus I 1 0 0 equal to 0, because A minus I B equal to 0 gives us solution 1 0 0. So, A minus I 1 0 0 equal to 0. So, this condition will be not valid if we choose 1 0 0. So, let us choose 0 1 0. Okay. So, let us take solution of a minus lambda I whole square b equal to 0 such that a minus lambda I b is not equal to 0 as 0 1 0. Okay. So, we take this solution and yeah, this is what I have written, b equal to b linear combination of these two vectors, and if we take this 1 0 0 transpose, then a minus lambda I b equal to 0. So, we take 0 0 1 transpose and then a minus lambda I b, which is a minus lambda I b is not equal to 0. This you can check, a minus lambda I b is not equal to 0 if you take b to be 0 0 1 vector. Okay. Thus, x 2 t is equal to e to the power lambda t, lambda is 1 here, and then what you have okay, x 2 t let us find. So, x 2 t we have to find. Okay. So, in order to find x 2 t, what we have, e to the power lambda t, that is e to the power t into we have taken 0 1 0. Okay. So, 0 1 0. Now, e to the power t we can write as e to the power t e to the power a minus I into t e to the power we have x 2 t equal to e to the power t into e to the power a minus. Okay. So, this is e to the power a t, yes, e to the power a t, because x 2 t is e to the power a t into 0 1 0, this is a solution of this. So, x to the power a minus lambda e to a minus I into t, this is e to the power t, a minus lambda I. So, 1 plus I plus a minus lambda I into 0 1 0 also we have to write. So, a minus lambda I t plus, yeah, and then a minus lambda I lambda whole is a minus lambda sorry a minus I here, a minus I whole square, this is b here and this is t here. So, t square a minus lambda I whole square by 2 factorial b and so on, this reduces to e to the power t I plus t times a minus I into b, and here also b, here also b. Okay. So, what we get e to the power t, then we have b is 0 1 0. So, 0 1 0 plus t times. So, you put the value of a minus I here, t times a minus I into b, b is equal to 0 1 0. What we get is e to the power t times t 1 0. So, e to the power t into t 1 0 is another solution of the equation, and for lambda equal to 2 we have the equation a minus 2 I b equal to 0. If we solve this, we will get b equal to 0 0 1 transpose. So, third solution is x 3 t equal to e to the power 2 t 0 0 1. So, thus we have 3 linearly independent solutions. How they are linearly independent? See, x 1 t, x 2 t, x 3 t are linearly independent because x 1 0 is 1 0 0, x 2 0 is 0 1 0, and x 3 0 is 0 0 1. You can see x 3 0 is 0 0 1, x 2 0 is 0 1 0, and x 1 0 is 1 0 0. So, these 3 vectors are linearly independent vectors in R cube, and therefore, x 1 t, x 2 t, x 3 t are linearly independent. Now, so the general solution we can write x t equal to c 1 times x 1 t plus c 2 times x 2 t plus c 3 times x 3 t, and when you add the 3 column vectors, what you get is this column vector. Okay. So, this is the general solution of the given vector differential equation. Now, in the case of this initial value problem, x dot equal to 2 1 3 0 2 2 0 2 minus 1 0 0 2 x 0 equal to 1 2 1, you can see that lambda equal to 2 is an eigenvalue of A with multiplicity 3. A is equal to 2 1 3 0 2 minus 1 0 0 2. It is an upper triangular matrix. So, its eigenvalues are its diagonal elements and which are 2 2 2. So, eigenvalues of A are 2 2 2, okay. That is lambda equal to 2 occurs with multiplicity 3. Now, eigenvector for lambda equal to 2 if you find, then you will see that A minus 2 I B equal to 0, okay, gives you a solution by B equal to 1 0 0. So, e to the power 2 t 1 0 0 is one linearly independent solution of x dot equal to A x. Since A has only one linearly independent eigenvector, we get one solution. The other linearly independent, to find other linearly independent solution, we find those vectors B for which A minus lambda I whole square B equal to 0 such that A minus lambda I B is not equal to 0, lambda is equal to 2 here. So, now consider A minus 2 I whole square B equal to 0, then we find, so A minus 2 I is this 2 1 3 2 1 3, okay. So, A minus 2 I will give you what? A minus 2 I will give you 0 1 3 0 0 minus 1 0 0 0, and when we multiply 0 1 3 0 0 minus 1 0 0 0, what we get? So, this will give you 0 0 0, first column is 0 0 0, when it is multiplied to rows will give you first column as 0, then 1 0 0, 1 0 0 will also give 0 0 0, and then 3 minus 1 0, 3 minus 1 0 will give what? 3 into 0 is 0, minus 1 into 1 is minus 1, and then 3 minus 1 0 will multiply to this, this is 0, this is 0, this is 0, and this is also 0. So, what we get? A minus 2 I whole square, this is, okay. So, A minus 2 I whole square B equal to 0, if you do, then what you will get? 0 0 so we get V3 equal to 0. That means B1 and B2 are arbitrary, okay. So, B1 and B2 are arbitrary means we can take B as 1 0 0, or we can take B as 0 1 0. Okay. Now, corresponding to lambda equal to 2, the one solution that we have got is what? 1 0 0. So, if you choose 1 0 0 here, if you choose 1 0 0 here, then A minus 2 I B will be equal to 0, okay, because we have already seen that. So, let us choose 0 1 0, okay, corresponding to lambda A minus 2 I square B equal to 0 and A minus 2 I B not equal to 0. So, if you choose B as 0 1 0, then A minus 2 I B will not be equal to 0. So, we can consider this vector, okay, and when you do this, then what will be x 2 t? So, x 2 t will be equal to e to the power a t into b, b is 0 1 0 we are taking, okay. So, e to the power 2 t and then e to the power a minus 2 t into a minus 2 I, a minus 2 I in t, okay, 0 1 0. So, this gives you what? E to the power 2 t times I plus a minus 2 I t and then 0 1 0. Okay, so, we get e to the power 2 t 0 1 0, okay, plus a minus 2 I. A minus 2 I is the matrix, a minus 2 I is the matrix 0 1 3 and then we have 0 0 minus 1, and then we have 0 0 0. Where is that? Into 0 1 0 into t. Okay. So, this is what we get. So, e to the power 2 t 0 1 0, and then be 0 1 0 when you multiply here, what you get 0 1 0 you multiply. So, you get 0 1 here, and 0 1 0 when you multiply here you get 0 0 1 0 you multiply here you get 0, and you get t here. So, what you get e to the power 2 t t 1 0. Okay. So, one solution is this we have got. Okay. Now, so we have x 2 t equal to e to the power 2 t t 1 0. This is one another solution. Now, we have to still get one more solution, because a minus 2 I whole square b has given only two linearly independent solutions. So, let us consider a minus 2 I whole cube b equal to 0. So, when you consider a minus 2 I whole cube b equal to 0, such that a minus 2 I square b is not equal to 0, then a minus 2 I whole cube b equal to 0 gives you what? A minus 2 I whole square, where we found a minus 2 I whole square is this. If you multiply again a minus 2 I, what you get? 0 0 minus 1 0 0 0 and 0 0 0, and we multiply to this 0 1 3, and we multiply 0 0 minus 1 0 0 0. Okay. So, this is a minus lambda I whole cube. So, what do you get? This first vector is column vector is 0. So, vector. So, we get 0. Second 1 0 0 gives you 0, and third is 3 minus 1 0. 3 minus 1 0 when you multiply here you get this. Okay. So, a minus lambda I whole cube b equal to 0. Okay. A minus lambda I whole a minus 2 I whole cube b equal to 0. When we do, what we get? 0 0 0 0 0 0 0 0 0, and then b 1 b 2 b 3 equal to 0. Okay. So, b 1 b 2 b 3 are arbitrary vectors here. Okay. So, now we can consider then b 1 b 2 b 3 is a linear combination of 1 0 0 0 1 0 and 0 0 1. Okay. So, 1 0 0 we already have got. 1 0 0 was a solution of a minus 2 I into b equal to 0. 0 1 0 we got as a solution of a minus 2 I whole square b equal to 0. So, here we want that vector for which a minus 2 I whole square b is not equal to 0. Okay. So, but a minus 2 I b cube equal to 0. So, this we cannot take, because for this vector a minus 2 I b equal to 0. So, a minus 2 I whole cube b will be equal to 0, and a minus 2 I whole square b will also be 0, and this vector also we cannot take. So, let us take 0 0 1. So, we take here b equal to 0 0 1, and for this we then find the solution, third solution x 3 t equal to e to the power a t into b. So, we get 0 0 1, and we write it as e to the power 2 t e to the power a minus 2 I into t 0 0 1, and then we write e to the power 2 t I plus a minus 2 t 2 I into t plus a minus 2 I whole square upon 2 factorial into t square. Other terms will vanish operating on 0 0 1. So, you know the value of the matrix a minus 2 I, you also know a minus 2 I whole square. So, substitute here, this I is identity matrix. When you take this product of these two matrices, this matrix into 0 0 1, what we get is this x cube x 3 t as e to the power 2 t 3 t minus half t square minus t 1. So, what we get x t now is a linear combination of these three linearly independent solutions x 1 t, x 2 t, x 3 t. Now, we use the initial condition. The initial condition is x 0 equal to 1 to 1. So, when we use x 0 equal to 1 to 1, we will have C 1 x 1 0, C 2 x 2 0, C 3 x 3 0. Okay. C 1 times. Now, x 1 0 is what? Yeah, you put t equal to 0 here. So, we get 1 0 0, and here you put t equal to 0, then but you get 0 1 0, and here you put t equal to 0, then you get 0 0 1. So, we get 1 0 0, 0 1 0 and 0 0 1. So, what we get is C 1 C 2 C 3. So, then C 1 C equal to 1, C 2 equal to 2, C 3 equal to 1. So, put these values of C 1 C 2 C 3 here, okay, you get the solution of the initial value problem. So, the solution of the initial value problem is x t equal to e to power 2 t times this column vector 1 plus 5 t minus half t square, 2 minus t and 1. So, this is how we solve the homogeneous vector differential equation with constant coefficients in the case where the characteristic equation has equal roots. So, in the next lecture we shall discuss non-homogeneous vector differential equation with constant coefficients. Thank you very much for your attention.